So coming to our topic, which is locating neutral axis for a cracked elastic section, we have a simply supported beam, the span of L, section with width of B and a total depth of H. There is some steel used, which is having the area of AS. Requirements are to locate neutral axis using transformed area method, and then to locate neutral axis using force equilibrium method. We discussed about it in our previous lecture, and today we'll be using them to locate our neutral axis. So under the applied load, there would be some tensile strains occurring in concrete, tensile strain in concrete and compression strain in concrete. Then we'll be having tensile strains in steel as well. Uh, Neutral axis is located at a distance c from the topmost fiber. Uh, the effective depth is d, which is a distance from the top fiber to the centroid of the steel used. Distance from the neutral axis to the centroid of the steel is d minus c. Total is d. This distance is c, so this distance is given as d minus c. Uh, we have a cracked section, so the strain profile will be continuing like this, but uh, it is not existing because concrete has already cracked and it cannot take any tensile stresses. So the all the tensile stresses will be taken by the steel, and stress in tensile steel is given by Fs. And if we multiply this Fs by the area of steel, we'll get the total force in the tensile force in the steel. And similarly, you can calculate the total tensile force in compression force in concrete, which is given by the compressive stress multiplied by the area. So total compressive stress is this is a triangle, so half base into height. Base is c, height is compressive stress half c into f compression, and then multiplying by the width of the beam. So this comes out to be the total compression force in concrete, which is in compression. uh, in this case, we are assuming that the concrete is cracked, so your tensile strain in concrete is greater than equal to the cracking strain, which is epsilon r, and then your strain in steel is less than yielding strain. Compression strain in concrete is less than proportionality limit strain of the concrete used. So we are in the linear elastic range, and we can use Hooke's law to calculate our stresses using strain. So stress is equal to strain in the model into modulus of elasticity of that material, which we already discussed. Uh, Coming to the first method, which is used to locate our neutral axis, which is transformed area method. Uh, in this case, we have three steps. First, we have to convert the area of steel into equivalent concrete area by multiplying it by the modular ratio, which is given by n, and modular ratio is basically um, modulus of elasticity of steel divided by modulus of elasticity of concrete. So if we multiply area of steel by this modular ratio, this will be an equivalent concrete area. Then we'll redraw the our cross section and then locate our neutral axis using first moment of area. So we have same section. We have compression strain in concrete, tension strain in concrete, which has already cracked, tensile strain in steel, compression force, we already discussed it. So um, there is an area, a concrete area which is in compression. It is still intact. It is taking compressive stresses. Um, Tensile stresses are taken by the steel, which is converted to equivalent concrete area by multiplying area of steel by the modular ratio. Uh, this is N into AS. N is the model ratio, AS is area of steel, and we have redrawn this section having compression concrete and equivalent concrete taking tension. Uh, so to locate the neutral axis location, which is at a distance of y bar from the topmost concrete fiber, which is equal to C. We take the top concrete fiber as the reference plane. So to locate neutral axis, we'll use first moment of area. This is the equation for first moment of area, summation of area 1 into its distance from reference plane, uh, plus area 2 into distance of um, its centroid from the reference plane divided by the total area, area 1 plus area 2 and so on. So y bar or C, so this is area 1, C into B, and then its distance of its centroid from top of fiber or reference plane, this is C divided by 2, so C into B into C divided by 2, plus second area, which is N into AS, multiplied by its distance of its centroid from the topmost fiber, which is given by D. So it is D, then divide by the total area, which is area 1, B into C, and then area 2, N into AS. So using this, simplifying this equation comes out to be BC squared divided by 2 plus NAS into C minus NASD. This is equal to 0. This is a quadratic equation. If you know the width of the beam B, if you know the area of steel AS, you know the modular ratio, you know the effective depth, you can easily solve this quadratic equation to get the value of C or y bar, which is the location of the neutral axis. Then there is another method, which is force equilibrium method. We can use this method as well to locate our neutral axis. We have to just apply the principle of equilibrium. We have compression force in concrete, tensile force in steel. Tensile force in steel is equal to compression force in concrete for equilibrium. Tensile force is given by area of steel multiplied by stresses in steel. Yes, Fs is equal to compression force in concrete is given by uh, the stresses in concrete multiplied by its area, which we already discussed over here. This is base of this uh, compression stress profile, which is half base into height, half C into F compression, half C into F compression multiplied by the width of the beam. So if we put in values of stresses in steel and stresses in concrete in terms of strain and modulus of elasticity, so it comes out to be AS into strain in steel multiplied by modulus of elasticity of steel. This is equal to half C into strain in concrete by multiplied by modulus of elasticity of concrete multiplied by B. Uh, Now in this equation we have three unknowns. We have strain in steel as unknown, strain in concrete as unknown, and then we have location of neutral axis or C, which is unknown. So we cannot solve this one equation for three unknowns. So we have to uh, represent strain in concrete and strain in steel in terms of C, so that we can solve for one unknown. Uh, so taking the same strain profile and using a similar triangle principle, strain in steel divided by D minus C is equal to strain in concrete divided by its base, which is C. If we simplify it, strain in steel is equal to strain in concrete divided by C into D minus C. We can put this value in our previous equation, and simplify it, and your final equation is BC squared divided by 2 plus NES C minus NESD, which is exactly the same equation as we calculated using transformed area method. So you can use any of the method to locate your neutral axis and then further calculate um, your stresses using flexure formula. Okay, so coming to the example which we solve using method discussed. So we have to actually calculate stresses, maximum stresses in concrete. It means stress in the topmost fiber of the concrete, and then stresses in steel. A simply supported beam is given, which is loaded by a moment of 80 kip fit, and we have to calculate the compressive stresses, which is the maximum compressive stresses in concrete, which will be occurring in the topmost concrete fiber, and then tensile stresses in steel, assuming it to be a cracked elastic section and modular ratio of 8. So our tensile strain in concrete has already exceeded its cracking strain. So concrete is cracked. Yeah, the section is in linear elastic limit. So we can use Hooke's law to calculate our stresses using strains. Section is 12 inches wide, 20 inches total depth, and effective depth of 17.5 inches. It is reinforced by four number 7 bars. Uh, this is the strain profile of our beam. And coming to a stress profile, we have compressive stresses in concrete, and then if we continue this stress profile, which is actually not occurring because concrete has already cracked, so we have shown it by a dotted line. But at this point we have compressive stress in steel, Fs, and if we represent it in terms of equivalent concrete stress, it will be Fs over N, because we are showing it on the stress profile of concrete. So it is actually Fs divided by N divided by modular ratio. Uh, we have to use a transformed area method to locate our neutral axis, and then we can calculate our stresses in concrete and steel. For that purpose, we have to first convert our steel into equivalent concrete area. Equivalent concrete area is equal to modular ratio into area of steel. Modular ratio is given, which is 8, and steel we have 4 number 7 bars. You can calculate the area of number 7 bar by using this equation pi r square, multiplying it by 4, you have the total area of steel, and multiplying it by the modular ratio, you have equivalent area of 19.2 inches. So you can redraw this section. You have concrete in compression and steel in tension, which is represented as equivalent concrete area as NAS, and its value is 19.2 inches. Now we will use same equation which we used earlier to locate our neutral axis. This simplification has already been discussed in previous slides. So you have this equation which is BC square divided by 2 plus NASC minus NAS into D. Now you have value for B, which is width of the beam, which is equal to 12. NAS is 19.2. D, which is effective depth, that is 17.5. So you have this quadratic equation, 6c square plus 19.2c minus 336 equal to 0, and solving it using your calculator, your c comes out to be 6.05 inches. So this is C, or which is equal to y bar, location of neutral axis, it comes out to be 6.05. Now you have located your neutral axis, and you can use your flexural formula to calculate stresses at any point. You just need the location of that point and the distance of that point from the neutral axis, and you can calculate your stresses in concrete, and similarly you can calculate stresses in steel. So but before going to the flexure formula, which is given by my over I, you already have a value for the moment, uh, applied moment, which is given. You have the location of neutral axis, so you can calculate y, which is distance of any point from the neutral axis at the point at which you want to calculate your stresses. And then you have to use um, a moment of inertia, and in this case, as we have cracked section, so you have to calculate cracked moment of inertia. You cannot use gross moment of inertia because concrete has already cracked, and um, calculating moment of inertia, you cannot consider concrete area below the neutral axis. So a crack moment of inertia is given by the moment of inertia of this transformed section, and you can calculate a moment of inertia for any section using this equation by the moment of inertia of one area multiplied by its area into its distance, distance of its centroid from the centroid of the whole section, which is the neutral axis, squared. So you have uh, section 1, or sorry, area 1, which is B into C, and then moment of inertia for this section is BC cubed divided by 12, because moment of inertia is given by BH cubed divided by 12. So in this case, you have B, H is C, so BC cubed divided by 12, and then its distance from the distance of its centroid from the centroid of the whole section. Centroid is at this location, which is neutral axis. Its centroid is at this location, so this distance is given by c divided by 2. So for this area, we have BC cubed divided by 12 is its moment of inertia into its area, which is B into C, and then its its area from the neutral axis, which is C. Actually, we have done minor mistake. It is C divided by 2 whole square, because it is yi square. So it is C divided by 2 whole square. So it will come out to be C square divided by 4. Then plus this is we can ignore the area of the moment of inertia of steel about its own axis, which is very small, plus area of steel, which is an AS multiplied by its distance of its centroid from the neutral axis squared, which is given by d minus c from neutral axis distance of its centroid. So d minus c squared, you can solve it, but uh, this has to be c squared divided by 4. Um, I will rectify it in the PDF notes, but we can consider the same value for this lecture right now. So your cracked section is 4067.28 inch raised to power 4. So now you have value of I. You can calculate value of any point from the neutral axis, y. You have applied moment, and you can use this equation to calculate stresses in concrete and stresses in steel. So for maximum stresses in concrete, which occurs at the topmost fiber, we have F comp, which is given by uh, M, which is 80 kip feet. We have converted it into kip inches by multiplying it by 12, because your distance is in inches and your moment of inertia is also in the unit of inches. So this is M. The uh, distance of topmost fiber from the neutral axis is 6.05. This is the topmost fiber where you will have maximum compressive stresses in concrete. So its distance from the neutral axis is 6.05, which we already calculated. So moment into 6.05 divided by moment of inertia. So your uh, compressive stresses in concrete, maximum compressive stress in concrete comes out to be 1.43 ksi. So if we are using 3000 psi concrete or 3 ksi concrete, it is less than 50% of maximum compressive stresses which concrete can take, or the compressive strength of concrete. And we discussed it in our previous lectures that um, till 40 to 50% of F-C, or compressive strength of concrete, concrete stays in linear elastic limit. So our assumption is true, which we assumed in the beginning of this example, that we are in linear elastic limit. So we are just below the linear elastic limit. Coming to the tensile stresses in steel, uh, Fs over N is given by My over I. M is the moment applied, I is the moment of inertia, and Y is the its location, or location of its centroid from the neutral axis, which we already discussed, which is D minus C. Uh, your Fs or N, which is modular ratio 8, is equal to 2.7, and your stresses in steel comes out to be 21.62 ksi. So if you are using 40 grade or 50 grade or 60 grade steel, your stresses in steel are significantly lower than the yielding stresses of steel, and you are in linear elastic limit. So this way you can calculate your stresses in concrete or stresses in steel. Now, if you want to calculate stresses at any other point, suppose we want to calculate stresses in concrete at some location which is located at a distance of 3 inches from the neutral axis, you can easily calculate the stresses at that location. Just put in the value of y equal to 3 inches. You have moment of inertia, and you can calculate compressive stress at that particular location. So you just need the location of that point, its distance from the neutral axis, and you can use this flexural formula to calculate stresses. Uh, So, with this, we come to the end of this lecture. Summarizing it, we have discussed two methods used to locate the neutral axis. First one is transformed area method.